right, good morning. How you guys doing? Doing all right? Okay, so I have a couple of announcements for you real quick. They are I don't have the full project instructions set yet, but I've got kind of my eyes on my target for you. So I wanted to comment on that. I also did post to the next kind of learning module. I think I put the due date, the class period after the exam, which is the one before Thanksgiving break. So that way, if you are pressed for time, you don't have to finish that before the exam. I was thinking I might give you this the next MATLAB assignment as a relatively simple assignment to import-export data, probably with relation to either a Redox system or in terms of a one of the solubility systems. I might put it a little later and then have it use have you use solver instead of just import export. So I'm still kind of wrapping up my ideas on that. And if I make something that's kind of involved, I'll probably put that beyond the exam as well. But if it's relatively straightforward, I might have it kind of just as a supplement to your homework. Okay, for the MATLAB, the big project, the class project, I have kind of collected my thoughts here, and I would like input from any of you if you are not feeling confident enough to tackle a project with MATLAB. I mean, I think many of you looked like you were making great progress with the previous assignment, but just in case, I'm also offering an alternative, and that would be to use Mintech. So in either case, the way I see coding in general and learning a software system is that there's going to be a lot of self-exploration. Learning how to code, gathering the resources, anytime you are developing code or learning a new software, there is that element of, okay, I want to do this thing, but how do I do it? And figuring that part out. So in either case, my aim is for you to be learning the tools in order to do some chemical analysis for some sort of equilibrium, geochemical, or other aquatic chemistry application. Okay, so with that in mind, what I'm going to do is I'm going to essentially generate context for something like, I think there's 7 of us, 7 students here, so probably like 8 to 10 chemical systems that we could characterize and solve for either like a PCPH for a speciation diagram, or as we'll get into the redox stuff, maybe a PE-pH diagram, or some other system where we are, maybe a solubility plot, where you'll have 8 or 10 potential systems that you could select from. And then if you're doing the MATLAB approach, I'm going to have you select one. Let me just do this. So my plan right now, and I'm going to formalize this into like a document for you, right? So that you'll have clear instructions. But the MATLAB case would be to select one, do all the analysis essentially in MATLAB, and or Excel as needed, but it needs to be solved and plotted in MATLAB at least. Then kind of provide a report on that. The alternative would be to approach this using Mintech. I guess I don't know if it's supposed to be all capitalized, or was it V? I don't remember if it was Mintec A or V Mintec, something like that. And then you would select, I'll probably give 4 or 5. So select several of the systems because it's most of the computation is on the back end, and it would be a matter of learning how to utilize all this, export essentially the files and the figures that are produced, and organize all that together into a report. So again, I will give more details and in both cases, probably I'll add a small task to provide a summary report for what you did. Okay, does that sound kind of reasonable? Okay. All right, so I'll probably give you more details on that on Thursday, but that's kind of what I'm expecting. Last time we left off on hardness, talking about a little bit about what is hardness so that we can talk about softening and how we use precipitation reactions to treat water in that way. So we get this general map of the US. If you visited different places, you might have noticed the hard or soft water. And of course, any particular place, maybe you'll find a well that has harder or softer water if you just have one particular change in geology or whatever. So this is generalization, but it holds pretty true. And so the question is, what do we do about it? And we have one of these like 12-step plans, except it's just 5 steps. And instead of, kicking a bad habit or something, it's softening your water. Okay, so in order to remove essentially calcium and magnesium is what we're after. Of course, there's a good chance that similar metals that have a kind of that behave in a similar way that would add to our hardness. There's not generally a lot of them in natural systems, but there's a decent chance they would also precipitate to an extent. Okay, so calcium and magnesium are the targets, and the first thing we need to do is remove CO2. We need to do that because that's going to be something that that's the added or extra alkalinity, and we need to kind of get a handle on that so that we can make use of our carbonate chemistry later. So we get rid of the CO2, and we can do that by adding lime. So calcium hydroxide, CaOH2, this is lime, and when we add that, we are going to precipitate calcium and carbonate, so calcium carbonate. It's kind of funny, we'll find in this system, we're trying to remove calcium and calcium and magnesium, so what do? We add a lot of calcium, and sometimes some magnesium. Actually, I don't know if we don't really need to add magnesium. But in theory here, we add about as much as we need to get rid of the CO2 that's already dissolved, and we get some precipitate in the form of calcium carbonate. So then we need to remove what we would call the calcium carbonate hardness, meaning we have some amount of calcium in the solution that's contributing to hardness, and it's associated with some carbonate that's already there. And this is going to look a little funny, given that we just added lime to get rid of the CO2. But here we have some calcium that's in solution. We have some bicarbonate that's already there. And so what do? We add lime. I'm just going to put the plus here to note that that's something that was not already there. And when we do that, turns out that, well, we're going to get our calcium carbonate again, but the deal is we are promoting the formation of that calcium carbonate because this is an equilibrium reaction, and we are now adding more calcium, essentially, to drive that reaction to the right. Okay, so with the added calcium there, we should be precipitating. And even though this is in equilibrium and we'll never get rid of all of the calcium here, for every lime we add, we should be at least removing 1 calcium. So we are a net benefit pushing that reaction over and removing a net amount of calcium. So it's kind of a bit counterintuitive there, but it works. Next up, we remove the magnesium carbonate hardness. It's a kind of the same deal. We have some magnesium in solution. We still have some bicarbonate. If we still have some bicarbonate, this would be relevant. And we're adding more lime. And this time what we're getting is calcium carbonate and a magnesium hydroxide, so MgOH2, and water. Okay, so again, we are hopefully precipitating as much calcium as we're adding, but in doing all this, we are encouraging the formation of this additional solid, and in this case, you can notice that the hydroxides are essentially coming from the lime that we're adding. All right, once we've done that, essentially we are doing those actions up until we no longer have any carbonate remaining to precipitate. So in one way we could look at that is we are, rather than removing calcium and magnesium here, we're actually removing the carbonate that could associate with them. And if you think back on our discussions about the alkalinity and electroneutrality and proton balance and all that stuff, you might recall that we could separate all of these cations and anions that don't directly affect pH in any way versus all the things that do, which would include all the carbonate species. And so in that sense, if we are changing one over here, we expect a corresponding change over there. And so keeping that in mind, this will start to make a little more sense that in order to affect some change in something that doesn't affect pH, we're going to affect something that does affect pH, or the proton balance, like bicarbonate. So if we are removing the calcium in that scenario to get that charge balance, that's kind of part of what's happening with the bicarbonate. Okay, so essentially in these two, well, really the first 3 steps, we're removing, the first would be the CO2 or the carbonic acid, but we are also removing that bicarbonate here as well when we do these pieces. Okay, so then once we pass that and we've gotten kind of across the threshold of the amount of stuff that we could do using the existing bicarbonate, then we go on to remove the calcium non-carbonate hardness. So whatever additional calcium is there that was beyond the bicarbonate that existed in the water already. So when we do that, what do? Well, we add some bicarbonate back. So it's kind of weird. We get rid of all this to remove some calcium, and then now we're trying to remove some more calcium, so we're going to add more carbonate in the form of this soda ash. So this is lime soda softening, or lime soda ash softening. So this would be this sodium, I guess bisodium carbonate, we would call soda ash. Okay, so when we do that, we're adding that CO3, which allows us to precipitate then calcium carbonate. We are also adding sodium to the water. Now, what you'll notice is on a charge balance kind of perspective, we are not removing a net amount of charge in terms of minerals in solution, because sodium we could look at as a mineral. But sodium doesn't really precipitate. The charge density is a lot smaller, so it functionally acts a lot different in water. And these are also going to be at concentrations that are rather low, so you might be thinking to yourself, oh no, people say don't have, low sodium XYZ foods are supposed to be healthy, right? Well, the amounts here are going to be way smaller than you would notice in sort of the food kind of scenarios. So it shouldn't be relevant in that regard, and it should be helping our general, just having that exchange is worth it, basically, for the quality of the water and the functions that it does for us. Okay, and the last step then would be removal of magnesium non-carbonate hardness, and it's kind of just like you might expect. Well, we have to add in some calcium in the form of lime and some of the soda ash so that we get all of the ingredients necessary to precipitate a bit more magnesium and also get rid of the calcium we just added. So we add, final step is adding lime and our soda to precipitate that kind of thing. The calcium carbonate and then magnesium hydroxides. All right, so putting all this together, this does a pretty good job of encouraging these precipitates to form, and then we're going to get a sludge that's got a lot of those solids in them. But these are equilibrium reactions, so we're never going to get to zero with these approaches. And there's kind of a hard limit. I think it's around, and maybe I have this on a slide. It's something like 25 to 30, somewhere around 20 to 30 milligrams per liter of calcium carbonate. Or hardness as CaCO3, in terms of what will end up remaining there no matter how hard we try. And if we flip back to kind of our hardness chart, anywhere below 60 is kind of recognized as very soft, or maybe below 50 depending on who you ask. So 30, even if I'm wrong and it's 35, it's in that range where it's nice and soft water. Not deionized, not distilled, but it's quite soft water. Okay, so I'm going to take us through an example. If we're to look at a system of water, I'm not doing this because I want you guys to be feeling capable to solve this particular example. I just want to give it some context if we were to jump into a water treatment classroom and do that. This is kind of what it would look like. So I'm going to go a little fast through this stuff, but just to kind of show you what kind of a process we could take. There's a book that I teach my water treatment classes out of, and we've got this example here with some water. We've got some CO2 in it, some calcium carbonate hardness, and I'm going to explain that in a little better detail in a moment. There's a graph we can take a look at. But so some calcium that's related to the carbonate, some magnesium that's related to the carbonate, and some of the non-carbonate calcium and magnesium. Okay, so then we are going to calculate how much lime we need, how much soda ash, and then how much calcium carbonate and magnesium hydroxides we will precipitate. So this table is kind of summarizing what we see, especially the this part is all the calculations to say how much do we need to treat this water. Given some water like this, we're going to find those other pieces in the following manner. Okay, so we'll take a look at each of our chemical species, and we can make this little bar chart that's got concentration on the x-axis. And it's kind of like a additive thing where we have some amount of bicarbonate here, and these two on the bottom here, this is all the cations and then all the anions. And if we list it out in this way, starting with bicarbonate, we can kind of take a look and say, okay, we've got 135 milligrams per liter of bicarbonate, and draw a line upwards to find how much of the calcium is related to the carbonate. Okay, so if we had a lot of carbonate, maybe we'd have all of our calcium in the calcium carbonate hardness, and then some of the magnesium as well. But in this case, we have more calcium than we have bicarbonate, and so we have some amount of calcium carbonate hardness. So this would be, as was written up there, this would kind of be that threshold where this is that non-carbonate hardness, NCH. It's all labeled up above here, so I'll stop labeling extra. We can divide it up then, and then come back to our 5 steps to say, okay, well, we did this amount of treatment for the calcium carbonate hardness, and then we ran out of bicarbonate, and so then we no longer need to do the magnesium carbonate hardness because there is no magnesium carbonate hardness. All the carbonate is gone before we get to that aspect of the hardness. So then we have calcium non-carbonate hardness and then magnesium non-carbonate hardness. So that kind of informs us how much of the stuff do we need. Sodium doesn't really relate to the hardness aspect, neither does the sulfate or the chloride. However, we can think for a moment about if this is all the species in our system, we should have charge neutrality, but it looks like we don't, so maybe we'd have to add some OH minus and we'd have some H plus here. But if there's that big of a gap, then that should be accommodated by OH minus. Maybe some other anions that aren't tracked here, but we could think about that and say, oh, okay, here's this amount of OH minus. And then we'd know how much H plus there is, which would be just a small amount. And we'd match that. So we could conceivably do all of those pieces with the skill sets and the things we've learned. But this is kind of a little bit of a brute force approach to say, okay, we've got this reaction that we need. It's going to precipitate some amount, so we're going to add that amount of stuff. This is just a simplified version, keeping only just the hardness related things. Looking at the stoichiometry, I mean, we kind of already saw this, but just to put it another way from the book that we've actually been using, the carbonate hardness for all of the carbonate stuff, lime is sufficient, right? We didn't have to add any of the soda for the carbonate related hardness. So if we had only the ability to add lime and we didn't have access to any soda ash, we could get some softening just by adding some lime for a typical system that has some bicarbonate. Okay, the non-carbonate, then we have to add some source of carbonate. And the stoichiometry is all there. Okay, so this is the example question. I said we're just going to skim real quickly through. There's a lot of text. I'm probably just going to highlight a thing or two and skip through it. The question here, though, is if we have some water utility treating some amount of water, 12 million gallons per day, we want to get it to the maximum softness, so the kind of the limit that this approach, the lime soda ash approach, will take it. Question is, how much lime and soda ash must the utility add? We'll notice that everything is normalized into milligrams per liter as CaCO3. That lets us deal with a mass unit that's already accounted for the molar conversions. It's convenient and very much an engineer type of thing to do. And then the other part of the question is what mass of sludge will be generated daily from that softening. Okay, so if we follow this, essentially we will start by removing that CO2. We can get that with Henry's law and the particular pH and stuff we're given, so we can figure out how much CO2 is there. That'll guide the first step. From then, we go on and take a look at that plot we showed to say, okay, well, how much calcium carbonate hardness there is. And we're essentially building that table. So this text is kind of walking us through building that table. Okay, now we can do the rest of it, row by row. We get the stoichiometry. Yeah. So basically explaining in words kind of what we talked about with that diagram. And it is tying in the stoichiometry a little more clearly. The stoichiometry is generally pretty simple, but we can just say like, okay, well, this amount of the calcium related to that carbonate, we add that amount of lime. Okay, so then we can get all the numbers calculated from there. goes on to give us the mass concentration that we need to add daily, and then the amount of sludge produced. So certainly something that we could calculate. This is not heavy chemistry in terms of compared to what we've been talking about. I just wanted to highlight the application of it into kind of a water treatment type of situation. Okay, I've got just a couple quick notes further on solubility and precipitation before we get on to redox chemistry. So that's what I want to do now. And I'm going to talk about metal hydroxides. There are plenty, but I'm just going to take ferrous iron as kind of a case example. So aluminum hydroxides are quite important. We see them often, especially if we're doing something like coagulation. Many metals will form these hydroxides like we talked about, and we may even be able to decide, okay, based on the type, the classification of our metals, we could then say, oh, this one's likely to have a hydroxide, this one's not so likely. So Fe2+, ferrous iron, will have 3 complexation reactions. This is going to take us from Fe2+, which would be, technically speaking, hydrated, right, with waters, and then putting those in equilibrium with adding the OH to it. So Fe2+, if we add an OH to it, that would give us FeOH+. And then we could go to FeOH2 with a 0 charge, and then finally FeOH3 with a minus charge. Those are the 3 that are important environmentally. We talked previously about how we can get these cumulative solubility product or equilibrium reaction constants. So we already covered that kind of stuff. So just as a reminder, these kind of build on each other, and then we can define them in those terms as a function of the OH minus added, but it's often more convenient to work with pH. So we kind of do this trick down here where we could set it up this way with the Fe2+ plus 2OH minus, but we could also invert it to deal with H+, like we're used to. And so we do that little trick and we get a final equation here where we have FeOH plus 2H plus in equilibrium with Fe2 plus and water, and getting a solubility product for that. That's going to be convenient when we want to assemble a plot that gives us a speciation diagram, right? What species of iron are we given a particular pH? So with that in mind, we can kind of ask ourselves 2 questions. One, given some total of iron, at what pH are we going to precipitate? So if we had 10 to the minus 4th moles per liter of iron, at what pH do we get precipitates forming? The other question would be, if we already have some of this amorphous iron hydroxides solids present, what is the speciation at a given pH? So if we have it in equilibrium with solid precipitates. So there's kind of 2 different ways to look at a system like this. We're going to approach number 1 first. We can't just simply put the total iron, that 10 to the minus 4th that we might say as an example. We can't put that just in equilibrium with our solubility product for iron and iron hydroxide. And the reason is because we have several different species that are going to have that equilibrium, right? Because our total iron is in 4 different forms. Some of it's in Fe2+, some of it's in that FeOH+, and so on. So if you recall, we can write the total mass balance like this because we have some fraction. The fraction that is in Fe2+ would be Fe2+ times 1. The fraction that is in FeOH+ is the concentration of Fe2+ times that constant divided by H+, and so on. So we're going to take a look at that in a moment. I'll just make a note that if the second case is true, then of course the total iron in solution will be set by the solubility product overall, because we know we're at equilibrium with the solid phase. So that the total will be set, and then we can look across different pHs to see, well, what portion of that total is in one form or the other. Okay, so starting with the first case where we have a set amount, 10 to the minus 4 is what the book uses, and we'll use that. Well, we could go through and calculate for every pH the speciation, right? Because we could set this equation up and solve for each portion given a known Fe total. We could use this equation, plug in a pH, and solve for what is this portion, what is that portion, and so on, right? We can do that. So if we were to do that and set up a table, this is what it would look like. In this case, we scan from pH 1 and go up by 2 all the way up to 11, and then we jump up to 13.5. Okay, one thing we'll notice is the book has a few numbers kind of struck through, and that's because at these pHs, we were actually exceeding our ion activity product, IAP, was greater than our solubility product. So we know that we had a case where we should be precipitating stuff, right? So if we calculate the IAP for every spot here and compare that with our known solubility product, which I don't know if it's written here, that's where we found trouble on these two cases, pH 9 and pH 11. So they recalculated at equilibrium where we have a new Fe total at those spots. Okay, one interesting thing is once we go up high enough pH, the iron hydroxide ends up redissolving, and that book saying that's because the anionic trihydroxy complex, the FeOH3 minus, is dominant, and that's a bit more soluble. Okay, so all that data is plotted here. If we were to graph it out and maybe take finer time point or pH points there. So this is kind of what we're seeing. We have a zone where everything below these lines is dissolved, and this is solid, right? So even though the total iron in solution would technically stay constant, I think I'm going to sneeze. So even though the total would never be more than 10 to the minus 4th, at some point we're going to have less total dissolved because the precipitates form. Okay, so this is that first question, right? If we have some amount of iron, at what pH do we form precipitates? This is our route to that solution, essentially taking a hold of this equation and solving it a bunch of times, right? And so that's one place where we can see a computational approach is quite helpful. Okay, the next would be what happens if we have solid iron in solution and we know it, okay? And then the question becomes, well, our equilibrium, we know that there is an equilibrium here. Fe2 plus is going to be in equilibrium with that. We have that solubility product, and we have some knowns that we can calculate. So if we start with the Fe2 plus, we can set up this solubility product here and say that, take the log of both sides because we've got the H plus squared there. That gives us a way to get on a log plot a linear relationship, right? So the log plots are really helpful for getting rid of those exponents. And so we end up getting a value here, log of Fe2 plus is equal to log of that first solubility product minus 2 times pH. So this is going to be a minus 2 slope that will define the threshold between Fe2 plus and the solid. Okay? And so for some pH, that'll be relevant, as we see right here. So I'll give this a little 1. And of course, we could draw that line further, but after some point, something else is going to become more important in terms of the solubility. So the next species then, FeOH plus. So we'll give this one a 2, follow the same procedure, and we get log K S1 minus pH. And so we have a -1 slope here. And of course, the relevant part is just this little corner. And we can see if we plot that line, we're essentially shaping another border for our system. Okay, next up, we've got a couple others, and some of the math I just put in pretty small just to remind you what we talked about a minute ago. We can do that same OH minus flipping to get the H plus, function of H plus, and dividing adding the reactions after doing that. We can calculate all that. We covered this previously. So essentially what we're doing is we're getting 2 equations. One is for this second one, the FeOH2, and ultimately yielding us this equation, which is a little larger here. So we're getting this equation that says that FeOH2 non-charged species is equal to log Ka2. So that's going to be this line right here. So not really raising or decreasing with pH, it's just a flat line there. And so whatever value that is, that's just what it is. And I don't even think that bounds the system at all. So it's kind of unimportant, turns out. And the last one, do the same stuff, a little more math, and we get to this log FeOH3 minus is equal to that log Ka3, or Ks3, excuse me, plus pH. So that's going to be this one here. Okay, so then we've defined all of our bounds, and here we have, because we know that there is some solid in solution, there's, in a way, an infinite source of that particular solid, allowing there to be as much of the other things as there can be until that solid is gone. So if we were to put this iron hydroxide solid, like a huge, huge block of it, and a little bit of acid at pH 2, well, it'll just continuously dissolve until there's no more stuff left, if the pH was kept at that level, right? So we can imagine that under certain circumstances, this stuff is super, super soluble, very highly acidic scenarios, for example, whereas other places, the most iron we could have is like 10 to the minus 7th. We hit the pH right. Most dissolved iron, excuse me. Okay, does that make sense? All right. So last thought then for precipitation is when we start forming a precipitate, it occurs by small particles starting to come together. And actually we kind of have to have some sort of particle in the first place for anything to begin. So we need some sort of a seed nuclei. Usually it's some sort of impurity in the solution. In most systems, that's not hard to find, some particle around, and then stuff will start congregating onto it. You can do interesting experiments where you supersaturate a solution, and I think a lot of kids in elementary years might have done this. You can heat water quite a bit, a solution of water and sugar quite a bit, in a nice clean glass bowl or something like that, where there's not many sources for nucleation, and so there will be a solution that is super saturated. Then you start cooling it back towards room temperature, but also keeping any nucleation stuff away. And then you dip in a little bit of fabric, or like a string or something, and then you can get crystal growth on it pretty quickly. Now, maybe I'm mixing and matching a couple there, but I guess you could put the string in and then cool it, and as it cools, you'll get the crystal growth. But that's kind of the point, right? Is the crystallization tends to occur on some particle, and there's going to be a few factors that are important. You can imagine surface area may be important. And really that has mostly to do with the surface energy of it. So the radii of the nuclei is important there. It's actually a kind of a similar phenomenon for boiling, for let's say water to start vaporizing. Kind of needs a little bit of something to grow the first bubbles on. So another much more dangerous experiment you could do with a microwave at home, please don't do this, is if you get really, really pure water and a really, really clean vessel, apparently you could microwave that, and you'd have to remove the bowl so you're not stirring or disturbing it, and end up with critically heated water, so well over 100 Celsius. As soon as that's disturbed, it's going to cause an explosion of superheated water, because it all wanted to vaporize and boil, and it's well high enough temperature to do so, but it didn't have any starting point to start the process, kind of. So you know, I don't think it's a big risk if you're like microwaving some water for tea or something. There's probably something in there, and if you got that hot, it would just start boiling, hopefully. But it is a potential risk, and could be quite a dangerous experiment to try on your own. So don't do that. Same kind of principle there, though, that for the bubble to appear and to grow and catalyze other ones, there needs to be some sort of disturbance. Okay, I'm not going to go far enough to really dig into depth on these processes here, but I'll say a couple other things. The kinetics in general for nucleation, they're going to be driven by what we call the saturation ratio. This is how much larger our ion activity product is compared to the solubility product, or the solubility constant. So if we just take a simple case that we talked about earlier today, right? This guy in equilibrium with calcium carbonate. The solubility product, I should write this the other way, right? Would make a little more sense for what I'm trying to say. Okay, we'll think about it this way. So when we define the solubility product, we typically do it this way, where the solubility, we call it a product because it's products over reactants. It's the product of the products over the product of the reactants, and we have a solid here, so it becomes 1, right? So it just becomes calcium times carbonate here. Okay, all that stuff you already know. We define our K that way, but the ion activity product is also defined that way. But these can be different if we have a supersaturation condition, or we could have something undersaturated. There are a couple other factors here, and we could look into that effective activity and things like that. So it's a little bit more complicated sometimes, but overall, this is how we define the saturation ratio, or this is the gist of it, okay? So if we have a saturation ratio where S is greater than 1, that's kind of the comparison between the IAP and the K, then we're supersaturated. So if we are way supersaturated, we have a very high S. So that would be this case. So this plot then is looking at the free energy for nucleation. And if the free energy is negative, that is highly spontaneous, right? And so when we are not supersaturated, we have a very positive free energy, meaning it's not at all spontaneous, right? If we have at saturation, or the saturation ratio is 1, it's not particularly spontaneous. If it's anything above 1, it will not be spontaneous up until we get to a certain radius for that nuclei. Then it becomes more and more spontaneous. So all that is really to say that that process does have some effect on the radius of some nucleation particle. Okay. We could look a little more into kind of the nature of how these crystals grow and how they become. There's some things we could study on that. But I'm going to leave it off at that point for now. Any questions on all that? Okay, so let's get to redox chemistry then. So redox. Redox is shorthand for reduction and oxidation reactions. It's kind of easier to say oxidation and reduction, or like that feels a little more natural, but redox, you know, compared to oxred, just sounds a little nicer, so redox it is. It's the shorthand. So any reaction that is essentially involving an electron transfer or change where the oxidation state of an atom is changed by the transfer of an electron is a redox reaction. So we can define oxidation and reduction. It can get a little squirrely in our minds if we're not careful, so we'll just take our time with this for a minute. We can say to oxidize something is to take its electrons away. So an oxidizer likes to take electrons from other things. It's greedy for electrons. So oxygen, we could think of as greedy for electrons, right? And it's rather electronegative. So we would imagine, and it is true that in general, highly electronegative species, atoms, tend to be oxidizers, at least if you have them in a scenario where they are not already satisfied. So if an oxidizer is a substance that takes electrons from other stuff, it then becomes reduced once it has oxidized something else, right? To reduce something is to give it electrons. So if an oxygen takes electrons, it just became reduced because now it has the electrons. So that can get a little squirrely. So I'm not planning to try to confuse you on this, just saying that. But you could imagine a case where you say, identify the species that are reduced here. That's a lot different than asking, identify the reducing species here. Because a reducer or a reducing agent is the thing that gives your electrons to other stuff and will then become oxidized. Okay, so oxidation, kind of big picture, oxidation is the loss of electrons. So if something is oxidized, it has lost its electrons. So probably the easiest thing to think about here is iron that is happily in a metal state, like metallic iron, and then it rusts with oxygen, usually aided by a little water, ends up rusting, and we end up with iron in probably a 2+ state. Now, I'll save the rest for when we get there, But the point here is oxygen is an oxidizing substance. It's going to take away some electrons from that iron. The iron is now in a 2+ or maybe even a 3+ state. Now it's rust, got some sort of iron oxide, probably is, probably O or whatever. Just leaving all that aside for now, the point is it's now in a positive state, meaning it has lost electrons or given them up. So iron in that case, the zero valent iron, the metallic iron, was oxidized, and the oxygen has taken those electrons and has then become transferred into some sort of reduced state. So in this case, if we had hypothetical, and I'm not sure this is a real oxide, but I think Fe2O3 might be, then we might say the Fe3+ is in a the Fe's are in a 3+ state and the oxygens are in a 2- state, each of them, which would give us a total of +6 charge for the irons and a -6 charge for the oxygens, if we were to think about it in that regard. We'll come back to all that and give proper examples, but that's the gist of it, right? The oxygens are now in a more electron-rich situation. They have been reduced because they were oxidizing, and the iron now has fewer electrons, has become oxidized, or was acting as a reducing agent there. Okay. Does that make sense? Clear enough? Not clear. Okay. How can I help? What's that? Wait, you said you'll wait for the example, or? Okay. Yeah, and I think that there will be plenty of examples. I'll just take my time and try to be clear with it. And we can always come back to this concept of oxidizing is stealing electrons from something else. Like the process of oxidizing is the process of taking away electrons. The process of reducing is the process of kind of forcing electrons onto something else, in that sense, if we're going to be forceful about it. Okay. Yeah, a lot of this depends on whose perspective are you taking, right? Are you looking at the what's happening to the molecule or the atom, or are you looking at that atom or molecule itself? Okay, quick little example of redox chemistry. One of my favorite fun chemistry YouTube channels, Explosions in Fire. He also has one called Extractions in Ire. I don't know a whole lot about him aside from he's an Australian guy that recently finished a PhD in chemistry of some sort and makes fun videos. But almost any explosion is a redox reaction. You're going to be oxidizing something, and that comes with a rapid transfer of electrons, and therefore in that a rapid release of energy. So if you wanted to take a look at some interesting redox chemistry, just a quick shout out and highlight for Explosions in Fire. Okay, so perhaps one thing that might help make this a little more clear is if we come back to what is an oxidation state, right? That's probably a place where we need to start here. So an oxidation state for a given atom is essentially the number of missing or extra electrons that an atom has relative to its elemental form. Now, when we talk about an elemental form, this is the form, if we just have that pure element, could be O2 or O3, could be H2 gas, could be helium, could be N2 gas, could be diamond or graphite, or my fun example, fullerene C60 or something like that. Could be iron, what we would call zero valent. Any of those that are existing in that as a pure substance, we we define that in some way, or it just kind of exists that in that regard, as a pure element at the zero valence state. Zero valent meaning it has no additional and it's not missing any electrons. So then if we have a substance in a non-zero state, iron 2+, for example, Fe2+, that's written sometimes as Fe with two Roman numerals in parentheses, or sometimes, and I think one of our books uses this convention, Fe with superscript 2 numerals. Now, it's not too different in simple cases as just writing Fe2+. If we just had Fe2+ in solution, we already know that that's the 2+ oxidation state. But in other cases where you might have some other stuff involved, maybe it makes sense to define that or be pretty clear. So simple cases are pretty easy to assign. If it's just the one ion, we kind of know. So sodium is in the 1+ state. Chloride is in the 1- state. Fluoride is in the 1- state. Magnesium 2+ is in a 2+ state. Does become a little more complicated. We have some rules to help us with this, but think of phosphate, right? What oxidation state is the P, the phosphorus? What oxidation state is the O? Each of those O's. How about sulfuric acid or HSO4-? What about nitrite? And how about nitrate? We can see that even just nitrite and nitrate, those are both 1- charges. They have a different amount of oxygens. So something's going to be in a different oxidation state in that, right? It's probably going to be the nitrogen, as we'll see. So we've got some rules, and I've got a couple tables to help us with those rules. But understanding these oxidation states is going to help us when we come back to think about, okay, what redox is happening, what change in oxidation state is occurring, right? So in general, if we have something complicated like this, and I have a nice set of rules that the book gives us, but before we even get there, we tend to assign electrons to the most greedy atoms. I say greedy, the most electronegative, right? So if we have something that contains oxygen, oxygen is pretty electronegative, right? Remembering that the periodic table, everything to the right and upwards becomes more and more electronegative, right? So if we did find a way to bond something with helium, we kind of expect helium to be the greediest of them all. But usually fluoride is kind of the most for anything normally we'd see. So we've got F is more electronegative than O, which is more electronegative than chloride, which is more than sulfur or nitrogen, which are kind of similar. I'm assuming by the way they wrote this. And those are all a lot larger than carbon. Carbon is a pretty neutral species. It's one of those on the 4, it's could have 4 extra or 4 less, and it's kind of like, it's 4 one way, half of 8 the other, right? It doesn't care. So that's not very electronegative. It's pretty neutral in that sense. But it is still a little more electronegative than hydrogen, and that is more so than metals, which we might call electropositive, because they would just kind of happily give away their electrons, apparently, depending on the state, I suppose. If they've already given them, maybe they can't easily give more. Okay, so that's kind of the scheme then. So if we use that and we take a look back at phosphate, well, we don't have any information on phosphorus itself, although we could probably look, and it's probably going to be grouped with these guys. So oxygen, though, is definitely over most other things. So we'd assign the electrons that are free and available to the oxygen there to find their oxidation states. Sulfur, like the sulfate here, likewise, we would first go send the oxygens to the electrons to the oxygen, and so on, right? We would, for nitrate and nitrite, we would say, okay, the electrons are going to be hogged by these guys, and then let nitrogen figure out the oxidation state from there. Okay, so let's take a look at the formal rules. Well, first of all, some elements are only going to have one oxidation state outside of like the zero valent. Others have two or more. So nitrogen has several that it can be in, carbon has many, sulfur, chloride. I think oxygen is almost always 2- if it's going to be in an oxidation state. So some of them are pretty limited. I think iron is relegated to pretty much 2+ and 3+, and of course 0. Okay, so the rules. For monatomic substances, so single atom substances, the oxidation states are equal to the charge, right? Mg2+, that's a 2+ oxidation state. Pretty obvious on that one. For everything except metal hydrides, so metals bonded with H+, or H, anything bound to H is assumed that the H has a +1 oxidation state. So we saw H is really not very electronegative. It's all the way on the left side of the periodic table. So it's going to almost always give away its electron so that it can satisfy somebody else's unpaired electron. And so when we have, let's say, HCl, what that's going to look like functionally is the H, as it shares these electrons, will kind of let those two electrons go over to the Cl side. Of course, in water, that dissociates and we get H+ and Cl-, right? But it's kind of like we have a plus charge here and a minus charge here. Right? Does that make sense? Okay. So it's kind of like who gets the paired electrons, right, within that molecule. And if we have H+ and it's bound to something aside from a metal, chances are the H is getting a +1 state. Okay, oxygen has an oxidation state of 2- in almost all substances. Okay, so I misspoke, and I should have known this. I thought about it already. It's often in the 2- state, like I mentioned, but we can also have peroxides. So anytime we hear an oxide, metal oxide or whatever, that's a 2-. Anytime we hear a peroxide, that's actually a 1-, which is that OO group. So hydrogen peroxide, H2O2, we could write as HOOH. That is each of those are in a 1- state. We also occasionally have a very fancy special thing. This is more of a radical situation, but a superoxide, if you ever see that, the oxygen is in a -1/2 state. Probably not too relevant, but this does explain if you do any kind of radical chemistry or photochemistry, you might find sometimes the superoxide radical anion is what it's called, O2.-, has an unpaired electron that means it's weird, it's a radical. Talk about that in a moment. But in order for that to achieve a O2 with 1-, they have to have each a -1/2 electron oxidation state. Okay, moving on. The next rule is in covalent compounds, the oxidation of state of each atom is the charge remaining when each paired electron is assigned completely to the more electronegative compound. So when we were thinking about nitrate and nitrite, we said oxygen is going to be the ones taking all the electrons. So we assign all the electrons that we can to those oxygens, and then what remains is kind of the resulting question. Okay, so if an electron pair is shared by two atoms of the same electronegativity, let's say a carbon-carbon bond, We just split between the two. Okay, next, the sum of oxidation states for atoms in multiatomic substances is 0 for molecules and equal to the formal charge for ions. So if it's not charged, it's not charged. Okay, pretty simple there. When multiple atoms of the same kind occur in a species, especially carbon in organic compounds, the element may have an average oxidation state that is the fractional value, because different carbon atoms have different oxidation states. So basically that's saying if you have a large and complicated molecule, you might have a carbon group on one side of the molecule that has a particular oxidation state, and another carbon on the other side of the molecule that's different, just because it's local environment, and ultimately that it kind of can make sense, and then you could just assign it an average. So even for phenol, apparently that's important. Okay, some examples here. We've got a bunch of nitrogen substances. This will help us clarify what's going on with the nitrate and nitrite. So we've got ammonia, NH4+. If we take that and we think about it, the H has to be in a +1. So we've got 4 +1s. That means the N has to be a 3-, right? So 4 - 3 gives us the 1+, right? So H2S, hydrogen sulfide. Well, if the H's are +1, then this sulfur has to be in a -2 state. Okay. We have lots that we could take a look at. Let's just skip down to nitrite and nitrate. So NO2-. Well, each oxygen is going to be in a -2 state. We're going to give them all the jurisdiction here. That means the nitrogen has to be in a +3 state. So if we take a look, we have nitrogen in several different states. We have a 3-. We have now a 3+. We have potentially a 4+ with NO2. And nitrate here, we're going to have a +5. So we could take a look at lots of these, lots of sulfur ones, lots of carbon ones. The phenol here, I think, is the average that we're talking about. It's going to be a little different, but carbons can do that. They're pretty flexible with their electrons. Okay, a few other examples over here on the right. So elemental carbon, talked about that. Graphite, diamond, fullerenes. Graphene is it's going to have some oxides on the edges, but it's almost also elemental. Sulfur, and so on. So lots of different examples here. Okay, ferrate is another one, Fe6+. Forgot about. So I think you get the picture. You've seen many of these compounds. You've seen many of these ions, and probably had some intuition about them, even if you didn't quite like stop and think about them all the way. So nitric oxide, just noticing it has that here too. That's N in a +1 state. Okay, a quick note on radical chemistry. I kind of already touched on it a little bit, but the radical is an unpaired electron. So if we've been talking about all these paired electrons where things are going to go like that, well, radicals are going to be really strange. They're not going to be very stable typically. So they're going to want to react with something really quickly. Now, if you end up with a situation with an unpaired electron, sometimes this requires some strange or kind of big event. But when you get that, maybe a photochemical event or something, then whenever that radical goes and reacts with something else, then that something else now probably has an unpaired electron, right? Under normal circumstances, unless a redox reaction occurs. So if you just have one reaction where a superoxide radical anion reacts with some methane, well, now the methane has an unpaired electron because of that transfer, right? In some way, that unpaired electron is transferring along until you have an event that can accommodate that into a change in oxidation state. And that's kind of the role of antioxidants. They typically will have a metal within them that is redox active, meaning that it can happily exchange, take, or give electrons as it's going. So in that type of a system, you kind of need an endpoint for the radical. So unless the radical meets another radical and they cancel, and now you have two unpaired electrons, makes one pair. Unless that's happening, you end up with a situation where you need something that can take that redox and change an electron oxidation state for it. So this is why radicals in the atmosphere live a long time, or can they're important for atmospheric chemistry, and they can go through lots and lots of reactions before they can find either another radical or something. So in general, radicals in the atmosphere last longer than in water for a few reasons like that. Polymerization reactions also quite important for the propagation of these radicals to cause polymers to link. It's also a concern for, in human health and stuff, the role for antioxidants having some balance. We face oxidation events. Our mitochondria are oxidizing things all the time on purpose to generate energy. So that's like by design. So there's some concern that appears pretty reasonable to me that having a diet with lots of polyunsaturated fatty acids, they've got a lot of unsaturated bonds here, they're oxidizable and can and will carry radicals and propagate it from one to the next. So if that's causing some damage, and the real concern is that you'll split these and end up forming formaldehydes, which is not good for health, if you have a lot of them around. So there's technical reasons that, whatever dietary stuff you might hear about with fats, there might be a technical reason that saturated fats are actually going to be better than highly unsaturated fats. Okay, I'm going to wrap up for today on this slide and say, when we take a look at a redox reaction, we're going to look at it in halves. We're going to have, we will take a half reaction approach. That's going to let us keep it a little simpler to look at what's happening with one particular piece of the reaction and a given electron transfer, and do that one piece at a time. And in part, that's because in a total reaction, we cannot actually have electrons in our stoichiometry, in our balance, because we're never going to produce or destroy electrons. So the full reaction should have 0 electrons. But to allow us to understand where they're going, we elaborate them and split these reactions in half and do the half reactions to kind of study them that way. So we have a reductant that becomes an oxidant plus an electron, is one way we could look at it. That would be the first half. The other half would be an oxidant that took the electron away and is now a reductant now that it has that electron. So a reductant is going to try to reduce something and take something's electron away. No, excuse me, sorry, I said that backwards. Reductant has electrons and is going to try to force them on somebody else. And so then it can become in a more of an oxidant and having given that electron away. We'll say it that way. The oxidant wants to take somebody's electron, so once it takes somebody's electron, it becomes now a more reducing type of agent. So hopefully that's a way to put those together. So then the net reaction then is the reductant plus an oxidant becomes an oxidant plus a reductant. I don't love the way that all comes out, but in relative terms, I guess it kind of makes sense. Has that helped at all? Or still have some questions? I think that would be correct to say a reductant is a reduced species because it's likely to reduce something else. Yeah. Okay. Anything else? Any other questions? Okay. All right. See you guys on Thursday.